So good morning, everyone, and welcome to this session on prioritizing technical debt as if time and money mattered. So this is a broad topic, and we're going to cover a lot of ground today. So let's jump right in and start by uncovering the forces that we all have to balance when building large-scale software systems. And these challenges of large-scale systems, they're very well captured in something called Lehman's laws of software evolution. So Lehman's laws of software evolution, they are of course not any real laws in the formal sense of the word. They are more like a set of accurate observations. And I would like to share two of them with you now to see if they resonate with your experience. So the first law of software evolution is the law of continuing change. And this is where Lehman claims that a system has to continuously adapt and evolve, or it will become progressively less useful over time. Do you recognize this? Yeah, that's the very reason why we keep adding new stuff, why we keep adding new features to our existing code bases, because we need to keep them relevant to our users. We need to respond to market needs. We might even have to respond to competitors. So successful software is never done. Now, what I want you to do is to note that there is some kind of tension, some kind of conflict to the second law of software evolution, and that's the law of increasing complexity. Well, Lehman claims that as a system evolves, its complexity will increase unless we actively try to reduce it. So what I find so fascinating here is that this sounds like a real challenge, right? On one hand, we have to continuously adapt and evolve our systems, but when we do that, they become more and more complicated, which in turn makes it harder and harder to respond to change. So it's a vicious circle that we need to control and break. And what I have found is that when we end up in that circle in a software project or when developing a product, what tends to happen is that we tend to miss the real root cause of the issue, and we tend to focus on symptoms instead of the real issues, because the symptoms are visible. And the symptoms we see, they depend on who we are, what our role is. So for example, technical leaders, they tend to see effects on the roadmap. They might see things like the lead times for implementing a new feature. They get longer and longer and longer. And as a consequence of that, we tend to lose predictability. It becomes very hard to guess when a particular feature will be done. So that's what the business sees. What our end users tend to experience is this. They tend to experience bugs, effects on the external quality of the software. And the real root causes, like technical debt, remain largely hidden, opaque, and obscured. So how can we bring visibility to technical debt? I think that's the most important question. Well, there have been several traditional approaches. One of them is to try to measure it. What if we could quantify technical debt and put a number on it? Then we can use that to make decisions. And this is an approach I've seen implemented several times, and I've never seen it work. And I would like to explain why. So one client that I worked with a couple of years ago, they had used a tool that's capable of quantifying technical debt. And the way these tools work, they're static analysis tools. So basically it's a tool, you take it, you put it on your code base, the tool scans your code, and each time you find some coding constructs that looks problematic according to a fixed rule set, they add a number to it. So for example, you might have a complex conditional statement. It takes you 2 hours to refactor that. So you have 2 hours of technical debt. Then you continue to scan and you find that, oh, we have a public method that lacks a comment. That takes 5 minutes to add. So now you have 2 hours and 5 minutes of technical debt, and so on. And the problem I've seen with that is this company I worked with, they took a tool like this and threw it at their 15-year-old code base. And this tool happily reported that on your 15-year-old code base, you've accumulated 4,000 years of technical debt. 4,000 years of technical debt on a 15-year-old code base. Let me put that into perspective for you. 4,000 years ago, that was here. That was the start of recorded history by the invention of writing. And I mean, I understand that a lot of that technical debt grew in parallel by having hundreds of developers working on the software. But still, how useful is that information? It's definitely depressing, but is it actionable? How do you act upon it? And that's where the problem starts, because what companies tend to do next is that they tend to put a quantitative goal on it. So a very common approach is that you say, all right, so we have this huge set of potential code quality issues and technical debt. The first thing we do is we throw away all recommendations. We don't have time for them. Next thing that goes is the warnings. So we can live with them. Let's get rid of them. Let's focus on the major issues that we have reported by the tool. And you often end up with lots of them. So some organizations might say, we have 7,000 major issues. Let's invest 3 months into bringing them down to just 5,000. And when I hear something like that, I always advise against it. Because to me, going from 7,000 issues down to 5,000, it's a little bit like choosing to jump from the 5th instead of the 7th floor. Most likely none of them are a good idea. And the reason I say this is because we need to consider what kind of behavior do we reinforce with a quantitative goal. Because software developers, like me, what we're going to do is we're going to optimize for what we're being measured on. So if we're being measured on a quantitative goal, what we're going to do is make sure we meet that goal. So we're going to pick the tasks that might look the easiest, that are most accessible, or the ones we are most familiar with. What's always lacking in a quantitative goal is the most important aspect when it comes to technical debt, and that is the business impact. So what I wanted to tell you with this introduction was that quantifying technical debt, first of all, it's simply not possible to do it from code alone, and quantifying technical debt simply isn't actionable. At the same time, it's a challenge that we need to solve. Because remember Lehman's law, we're always going to have this trade-off between improving existing code, refactoring and redesigning, versus adding new features, what the business really wants. So we definitely need to prioritize, but how? Those of you who might have read one of my books, you know that I'm a big fan of version control data. And the reason I'm a big fan of version control data is because it's a virtual goldmine of information on how our system evolves. You see a simple example from Git here. If we look into our version control data, we can actually get a time dimension into the evolution of our code base. We can see which pieces of code that were worked on and when they were worked on. And we can even see which direction they evolve in. I'm going to cover that very soon. And what's also interesting is that version control data, it has traditionally just been used as an overly complicated backup system, occasionally a collaboration tool. But in reality, it's a wonderful behavioral data source on us, our development organization. So let me try to make this specific, but walking you through a case study of prioritizing technical debt. And I want to do this case study on a code base that I think a lot of you might actually carry around in your pocket as I speak. I'm talking about Android. More specifically, I'm talking about the part of Android known as the platform framework base. The platform framework base, it's a pretty large code base, 3 million lines of code, most of it written in Java, and thousands of developers. And the visualization that you see here is something I call a hotspot analysis, which is like the workhorse for prioritizing technical debt. So let me walk you through the visualization so you know what you see. First of all, I would like to focus on the large circles, the ones that blink on screen right now. Each one of those circles represents a top-level folder in the code base. Right, so if this was your code, you will recognize the names of those folders as important subsystems or high-level components. It's also an interactive visualization, so I can zoom in to any level of detail that I'm interested in. And once I get to the lowest level of detail, I see that each file with source code is visualized as a circle. And you see that the circles, they have different size. That's because the size is used to represent the number of lines of code. So the more code we have in a module, the larger the circle. So the number of lines of code is something we can use as a very rough complexity dimension, right? Because there is a strong correlation between lines of code and actual code complexity. We're going to talk more about code complexity soon. However, what I would like to point out is that the complexity dimension is the least important aspect when prioritizing technical debt. And the reason I say this is because just some code is complicated doesn't mean it's technical debt. It's only technical debt if we need to work with it. So we need to figure out, does this code complexity, does it actually impact us? And this is data that we can pull out of our version control history. We can look at the change frequency of each piece of code. That is, how many changes do we do to that code? How many commits do we do? And we can calculate that and use color to visualize it. So the more red it is, the higher the development activity. And when you combine these two dimensions, we can identify hotspots, which are complicated code that we have to work with often. Now, once we have identified a hotspot, we need to dig a little bit deeper and see, all right, what degree of technical debt do we actually have here, so that we know what to do. And what I tend to do is that technical debt is multifaceted. So there isn't a single metric, there isn't a single measure we can use. What I use instead is a concept I call code health. And you have a link here at the bottom of the page where you can read a bit more about this. But what I typically do is I investigate specific aspects of the code and design that are known to impact the maintenance costs and the risk for defects. So just to give you some examples, it might be things like low cohesion. Is this module doing too many things, right? Another thing might be deeply nested logic. That's when you have if statements, inside other if statements, and so on. Which is a construct that we know from research is responsible for roughly 20% of all programming mistakes. And then we have the more general pattern that I describe in the link at the bottom, which is a bumpy road code smell. A bumpy road is simply when you have multiple blocks of deeply nested logic inside the same function. And the idea is that just like driving your car or bike on a bumpy road, that will slow down your driving. It's the same thing with code. If you have code that shows the bumpy road pattern, it will take you longer to understand it, which makes it harder and harder to respond to change. All right, so I try to identify these symptoms of low code health, and if I find them, I know I have an issue. The next thing I would like to know now is, all right, but what happens to this hotspot over time? Maybe it's a hotspot because the organization has already started to refactor it. So that's the reason for the high amount of development activity. This is something we can answer with version control data too. So what I do when I find a hotspot is I go to my version control data and I pull out each historic revision of that code. And then I measure the code complexity at each point in time and I plot it in a trend like this. And in this case, you see the blue line shows the number of lines of code over time. And we see that there is a growth. It's growing and growing, that hotspot. But the red line shows the nesting complexity. How deep is the nested logic in that code? And we see that it decreases quite rapidly. And that seems to indicate that this hotspot is a growing problem. So if I find a hotspot that is a growing problem and has symptoms of low code health, then I know that I found a refactoring candidate. And if I refactor that code, it's very likely that I get a real payoff. So the question is, of course, who would like to have that refactoring task? The Activity Manager service, the hotspot here in Android, is a gigantic file with 20,000 lines of code. And if we look at the version control data, we see that there have been 74 developers working on that code over the past 3 months. So that means we cannot really branch out and spend a couple of weeks refactoring the code because we will never, ever be able to merge it back, right? So what do? Well, the technique I use when I come across complex hotspots is something I call a hotspot X-ray. The way it works is that I take the hotspot, I parse it into separate function blocks, and then I look at the Git log, where do each commit hit over time, and I sum it up, and I get hotspots on a function level. And this is the data I use to prioritize a starting point for paying down technical debt. Let's see the specific data for the Android hotspot. So what you see here is the local hotspots found by the X-ray technique. And we see that hotspot number 1 on a method level is a method called handle message. We see in the change frequency column that handle message has been modified 96 times just over the past year. So like twice a week, some developer is impacted by that technical debt in that code. And the last column that says cyclomatic complexity, that's another pretty simple code complexity metric. It basically calculates the number of logical paths through that function. And it's a good indicator of how many unit tests would you need to cover just that function. You would need at least 106 unit tests, which kind of indicates that this is overly complicated code. We also see that handle message is a pretty large function, 500 lines of code. 500 lines of code, it's a lot for a single function, isn't it? It is. But it's definitely less than 20,000 lines of code, which was size of a total hotspot. And it's absolutely less than 3 million lines of code, which was size of a total system. So more important, we're now at the level where we can act upon this information and do a focused refactoring based on data from how code actually evolves and how we work with it. I'm going to return to the hotspots soon, but before I do that, I want to make sure that I manage to explain why hotspots work so well to prioritize technical debt. In fact, hotspots send a positive message. Hotspot tells you that you know you don't have to fix all your technical debt. And this is the reason. So please watch carefully, because this might be the most important slide in the presentation. So what you see here at the top are 3 different graphs from 3 different code bases. They all show the same kind of data. On the x-axis, you have each file in the system. And those files are sorted according to the change frequency. That is how many commits, how many changes you do to that code. And the number of commits is what you see on the y-axis. Now, if you look at the 3 examples, you see that they are from radically different code bases, right? Developed by different organizations, targeting different domains, different programming languages, different developers, different lifetime spans. Everything is different. And yet, they all show exactly the same pattern. They show a power law distribution. And this is something that I have found in every single code base that I've analyzed so far. And I've probably analyzed more than 300 code bases by now. So this seems to be the way software evolves. And this is important for us because it explains where hotspots work so well. Because what this basically means is that most of our code is going to be in the long tail. So it's going to be code that's rarely, if ever, touched. So those are the parts of the code where we can actually live with a certain degree of technical debt. Most development activity, on the other hand, is in a small part of the code at the head of that power law curve, right? And that's the hotspots. And even a minor amount of technical debt in a hotspot can quickly become really, really expensive. So using hotspots, we can identify the head of that curve. But there's a little bit more on it, because what this whole behavioral perspective on code does is that it helps us put code quality into context. And I have a chapter in my last book, Software Design X-Rays, that is, I call Your Best Bug Fix is Time. And what I did in that chapter was that I referenced some research that looked at how aging and stability impacts correctness. And what the researchers found was basically that code that has been stable for more than a year had roughly 1/3 fewer defects than code that had been modified more recently. So what this basically means is that code that's been stable for a long time is more likely to be correct. And before we move on, let's consider, why does code grow stable? Why do we stop changing a piece of code? Well, there are 2 likely reasons. The first reason is, of course, that it might be dead code, code that isn't used. And I have to admit, this is my favorite code, because dead code can be deleted, and less code is always better. So dead code is wonderful to find. The second reason is, of course, that it might be code that's actually used, but dead code, it might also be very complicated. It might have several code quality issues, but it might have been debugged into functionality. It might have been battle tested. It's proven in use. It just does its job. So that kind of code is also quite nice to have, right? And what hotspots do is that they help us separate our large code bases into the stable parts of the code that are likely to be correct, where we shouldn't necessarily focus proactive refactorings, versus the more volatile parts of the code, where code quality and keeping technical debt to a minimum is really, really important. When I talk about technical debt, people often mention legacy code. So I wanted to make a comparison because technical debt and legacy code are not the same thing. So what is legacy code? Well, legacy code to me is typical to describe code that, first of all, lacks in quality, and second, and more important, code that we didn't write ourselves. And the second point is really key here. So I like to share one of my stories with you. So this is something that happened to me a couple of years ago. I was working with one of my clients, and I did a workshop for them. I do lots of workshops around behavioral code analysis and hotspots. And as part of the workshop, we analyzed their 2 code bases. And we looked at the code bases, we identified the hotspots, we measured code health and all that stuff. And the code bases both looked pretty good. There were some minor issues, but no larger concern. So we spent the day working through that. And towards the end of the day, one of the participants said to me that, hey, you know, Adam, we actually have a 3rd code base as well. So I said, oh, wonderful, let's analyze that one as well. And he said, no, we don't have to do that. I said, why not? Because we know that 3rd code base, it's a mess. It's going to be a complete mess. So I said, interesting. Now we really have to analyze it. So we took that code base, analyzed it, identified the hotspots, and looked at the code health. And guess what? It turned out to be virtually no objective difference compared to the other code bases. They were all of equally good quality. And at first, the team couldn't believe this. We had to pick up code samples and compare them. But we finally agreed that, yes, there is really no objective difference. So why did they have this idea that the 3rd code base should be much worse? Why should it be a mess? It turned out that the reason that code was hard to understand was because it wasn't written by that team. It was written by a completely different team in a different part of the organization. And that team has since been disbanded, and this team inherited that code base. So the reason they found it hard to understand was not because of any technical properties, but due to unfamiliarity with the domain and with the solution. And I find this fascinating because it's all about system mastery. How well do we know the existing code? And I get inspired by that, and I start to think, how can we use behavioral code analysis to answer this question? How quick can we take your code base and turn it into legacy code? The reason we can do this is because version control data is social data. If we look at our example from Git here, we see that Git knows exactly which developer that wrote which piece of code and when they did it. So this is something we can use to reason about things like knowledge distribution. Let's look at an example from a different code base. This is ASP.NET MVC Core from Microsoft. So it's a framework used to build dynamic web applications. And it's the same visualization style as we used for hotspots, only now the colors of each file carry a different meaning. Blue means that this is code written by the current team. So these are the parts of the code where we have active, detailed knowledge. The different shades of gray that you see, that's code written by former contributors. So these are the parts of the code where we might have some knowledge loss. We might not necessarily understand all the details because we haven't written that code ourselves. And what we can do with behavioral code analysis is that we can simply simulate the impact. What happens if a specific developer or development team is offboarded? So I did this simulation on ASP.NET MVC Core. I simply identified one core developer and said, let's see what happens if this developer leaves. So I'm going to show you to the right, the impact. So this is the impact if a single developer leaves, if the wrong person leaves. It's simulated in red here. That's all the parts of the code where you will lose detailed knowledge. Would you be worried if this was your code? I definitely would. But using behavioral code analysis, we can now act upon this data. If we use this proactively as a simulation, we can simply say that, all right, let's look for some patterns here. You see in the picture to the right that we seem to lose most knowledge in the integration tests. Lots of red there. So maybe I can use this to direct an onboarding effort to the integration tests. What I also find interesting is that I tend to combine these social metrics with the technical metrics. So if I find that a hotspot with low code health gets abandoned, that is the main developer leaves, then I know that we have a real issue here, because it's going to be relevant code, it's a hotspot, it's complex, has low code health, and we lose detailed knowledge. So maybe I would use this to pair together the developer that's leaving with someone that's staying and have them refactor the code together to mitigate an upcoming offboarding risk. So I sometimes drive refactorings via these social metrics rather than just the technical ones. So what I wanted to say with this section was that I wanted to highlight that there is so much more to code complexity than just the code itself. In particular, social factors influence how we perceive a code base. And in particular, we tend to overestimate the complexity of unfamiliar code. Now, before I move on to the last section of my talk, I wanted to show you what tools I use, because I hope you get inspired to try this out on your own code. And I have to tell you that when I started to work on these analyses like 10 years ago, there weren't any tools available to do this kind of analysis I wanted to do. So I had to write my own. And I decided to open source my first tool suite. It's a tool I call CodeMat. It's available on my GitHub. It's open source, completely free. It's a command line tool. So if you're interested in that, that might be an easy starting point. What I've been working on for the past 5 years is a tool called CodeSyn. So CodeSyn automates all these analyses. It also comes with an automated code health measurement and code review and all that stuff. And CodeSyn is available at codesyn.io. So if you enjoy these analyses, consider to have a look at CodeSyn and support it. What I also want to point out is that you can actually get quite far with just a simple Git client. So I have several examples on that in my Software Design X-Rays book. And I just want to show you my favorite Git command here. Did you know that if you type git log with the -l flag, then you can specify a function inside a file and have Git trace the evolution of that function? And that basically gives you something like the basics for a simple X-ray directly from the command line. All right, you're getting the link at the end of the session too. There's one more thing I want to talk about. I wanted to talk about this, microservices. And the reason I want to talk about microservices is because when I started to do public workshops on behavioral code analysis and hotspots, it was like 5 years ago, most organizations were considering or had started a move towards microservice architectures, but it was still considered a pretty new style. These days, virtually everyone is doing some shape of microservices. And this is important to us, because what it means is that tomorrow's legacy code is going to be microservices. So let's stay ahead and see how we can apply these techniques to microservices. What I find interesting when analyzing microservice architectures is that we can use all those technical metrics, right? And they are valuable in microservices too. But my key point is that in a microservice architecture, the most important aspects of the architecture are not necessarily properties of the code, but properties of the system. And what I mean by that is that it's often more important to identify things like implicit dependencies between services or potential dependencies between different teams, everything that prevents you from iterating quick with your architecture. So let me show you what I mean by that, but turning to a different case study. This is a system called Spinnaker. So Spinnaker is an open source continuous delivery platform developed by Netflix and Google. It's claimed to be a microservice architecture, consists of roughly 35 different microservices located in 35 different Git repositories. So what you do in this visualization is a hotspot analysis of all those microservices. So the top level structure here, the large bubbles at the top that says Stack, Orca, Cloud Driver, and so on, these are actual microservices, and they represent the code in a single Git repository. So we're viewing the code across 35 Git repositories here. What I also want to point out, almost as a side note, is that this code is written by seven different programming languages: the Groovy, Java, Golang, TypeScript, and so on. So what I want to point out is that a hotspot analysis is language neutral because it's based on version control data, which doesn't know any programming languages. So we can get this holistic overview of our hotspots no matter what programming language we use. And I think this is important because modern systems tend to be polyglot. All right, in our microservice architecture, the important level of analysis is not necessarily the file level, right? So what I tend to do is I tend to take the code for one service and I tend to aggregate it and aggregate all the contributions to it so that I can measure hotspots on an architectural level. So what you see in this visualization is an aggregation where each bubble represents a whole microservice, right? So I've gathered and aggregated the Git log and the code complexity and the lines of code and everything. And I can, of course, use this to detect the hotspots at an architectural level. And I can do the same thing with complexity trends, right? So I can see hotspots that tend to evolve in an overly complicated direction. And I can use that to identify hotspots that might, services that might have to be split or might have to be refactored. That's definitely possible. But we have to be open with the limitations of hotspot analysis too. Because a hotspot analysis doesn't really help us in evaluating what happens between the services. And often that's just as important. So how can we highlight the dependencies in something like a microservice architecture or any architecture on an architectural level? Well, the technique I've been using, because we have to remember that on Spinnaker, the code is in multiple Git repositories. So what I tend to use is I tend to look at features and tickets. So I use a concept I call change coupling. And I like to explain what change coupling is, because change coupling is very, very different from the way we typically look at coupling in a system. Typically, when we developers talk about coupling, we mean a dependency, right? I have some code here that uses some code over here. Change coupling is different because it cannot be measured from code. It can only be measured from the evolution of code. So what I do here in this example is you see three different services here. The first time I'm adding a new feature, I'm modifying the subscription service and the sign-up service. The next time I'm adding another feature, I modify a different service. The third time I add a new feature, I'm modifying the subscription service and the sign-up service together again. So if this pattern continues over time, then we know that there has to be some kind of a logical relationship with the subscription service and the sign-up service, because they're always modified together, right? So this is what I use to highlight the implicit dependencies between different microservices, the logical change dependencies. And we can use this to reason about the cost and impact of change. So if you look at this graph, what you see here, the nodes, each one of those labels represent a specific microservice in Spinnaker, and the connecting lines, they represent the change coupling dependencies. And what we see here is that there seems to be a cluster of microservices that are often modified together. And then there's a service on the left-hand side called Roscoe that also seems to evolve together with the bakery service. Is this good or bad? Well, it depends. It depends on things like this. What if these services are owned, operated, and developed by different teams? What would that mean? This kind of leads us to one of the most common questions I tend to get when I talk about this. And that is, should we use component teams or should we use feature teams, right? We kind of tried both and none of them really seems to work. So let me explain this, because change coupling gives us a lens where we can kind of highlight these costs. So what typically tends to happen is that many organizations, they started up with component teams. And what happens with component teams, if you have dependencies between different components, is that you tend to get very, very long lead times, right? Because when implementing a new feature, you need to coordinate around changed APIs, you need to coordinate between different teams, and it simply takes a long time. So organizations often choose to reorganize into feature teams. And what tends to happen now is that the situation gets even worse, because suddenly everything becomes a potential coordination bottlenecks, and you have 5 different teams working the same parts of the code all the time. So the way to resolve this is to make sure you achieve that balance between your architecture, your organization, and the business problem we are trying to solve. And I like to read one of my favorite quotes. It's from a book called The Unicorn Project that came out earlier this year. It's a really good book. I highly recommend it. And in that book, Jin Kim writes that simplicity is important because simplicity enables locality. And locality in our code is what keeps systems loosely coupled, enabling us to deliver features faster. And if we look at the example I have on change coupling there, we see that we're actually violating the locality of change, right? We have a bunch of services operated by the same team. That's good. That's locality of change, right? This balance between architecture and organizational ownership. But then we have the Roscoe team to the left, and we have a dependency between the Roscoe team and the bakery team. And that kind of violates that the locality of change, which tends to lead to long lead times and quite an expensive architecture. So I hope this presentation has showed you what's possible by embracing behavioral code analysis. We can use it to identify hotspots in our code. We can use those hotspots to drill deeper using the X-ray technique so that we can prioritize specific starting points for paying down technical debt. But it doesn't stop there. We can also scale it up to the architectural level and reason about hotspots on an architectural level, as well as finding implicit dependencies between both code and people. And I like to point out that a behavioral code analysis doesn't really replace anything. A behavioral code analysis is there as a complement. It's there to complement you and your existing expertise, because large-scale software development is incredibly complicated. And I like to think that we need all the support we can get. And I hope that this session has inspired you to dive deeper into the topic. And if you're interested in reading more, I'll be hanging out here and answering a bunch of questions. Also have a new book called Software Design X-Rays that goes through all these techniques and many, many more. If you're interested in having a look at some real examples of trying this on your own code, then I recommend to check out codebases.io. We have some public analysis samples there. We can navigate some famous open source projects and look for hotspots there. I also blog about this regularly at codebases.com and adamtornhill.com. And I'm Adam Tornhill at Twitter. So before I take questions, I just want to take this opportunity and say thanks. Thanks a lot for listening to me, and may the code be with you. Thank you very much, and back to the studio.